welcome to the University of Hawaii Institute for Astronomy. There's my one. Pukalani building here on Maui. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist, and one of the things I get to do around here is put together these talks, which I find pretty cool, and I hope you do too. And then occasionally I get to impose what I want to talk about on the talks, and that's what's happening today. Is I wanted to talk about properties of asteroids. All right, so first of all, the couple of announcements. The next talk will be will be on Friday, June 13th. Yeah, but I wasn't introducing myself. That's my error for next. All right, so Friday, June 13th. And also tonight, remember, there is this possible meteor shower. I'm going to be honest and warn you. It could be a complete dud, but it also could be really good. They're saying that they think that we're going to go through this debris field. The predictions are 0 per hour to 1,000 per hour. Okay? So you get an idea of the uncertainty. But they think that we should see at least a few extra shooting stars, meteorites, or meteors. Possibly meteorites, but mostly we'll see meteors. All right? So properties of asteroids. This is a two-bedroom ranch. Very quiet neighborhood. All right, yeah, sorry, Mr. DeVay, Graham DeVay, some of you know him, posted something about that on Facebook, so I thought I would do that for him. But all right, so let's start off with, what is an asteroid? How many of you know what an asteroid is? Not surprising, okay? About 50%. Let's take it real slow. Let's first talk about planets. And what are planets? Does everyone here know what a planet is? Okay? Can anyone point at a planet right now? Exactly. Okay, good. No. But to the ancient astronomers, to the let's say the Babylonians, Earth was not really a planet. What they saw was these stars that moved, that didn't stay in the same place in the sky relative to the other stars. And so they called them planets, which is basically stars that wander. And there were just a few of them. And they wrote down where they were and what time. And later we learned what they are is objects like the Earth that orbit the sun, but with slightly different orbits. But going back to their time, now this is Mars. This is actually a simulation. If anyone has heard of the program Stellarium, it's free software. And each one of these steps is 1 day. I'm going to dim the lights in here. There we go. Air conditioning. Okay, I'll let you guys fight about that. And if it's too hot, open a window. That's the best thing. Yes. Okay, so basically this is Mars, and this is what it would really look like. About halfway through the simulation, I think, would be today. And it's just one step at a time. One step is 1 day. So before the invention of Facebook, internet, television, radio, staring at the campfire, there were a lot of reruns. And so they would look up at the sky, and they noticed Mars moving around, and they noticed Jupiter moving around. Okay? So it's just, these are planets that wander, or stars that wander. All right? Well, asteroids are things that we need a telescope to see. So this is our first little piece of what they are. You need a telescope. And when Galileo pointed a telescope in the sky in 1609, he opened up the whole solar system of asteroids to us. Okay? And the first asteroid was not discovered until 1801. And sort of the definition to work with there at this point is that an asteroid appears as a dot. But a planet, you would actually see some spatial resolution. You would see that it was, instead of just a pinpoint of light that moved, it was a round dot. You could see some structure. When you look at Saturn, you can see the rings. So you can see more than just a single pinpoint of light when you look through a telescope at an asteroid. Or when you look at a planet. When you look at an asteroid, you see a single point of light. That was the first sort of distinction. All right? And so this is sort of what we see. This is actually an asteroid that should be very interesting to everyone. This is 1950 DA. Does anyone know what 1950 DA's significance is? Yeah, it came very close to the Earth. For a while, it was considered the biggest threat for impact because of its size and its probability of impact. It was still a very small probability of impact, and I think now it's still considered, if not the highest threat, it's still considered a threat. And so this is the idea is this is what an asteroid looks like through a telescope. Now all of these are stars. The stars are actually smaller than 1 pixel on the telescope. The reason some of them look bigger is because the light's kind of being blurred around on the image. So we're still not getting any shape information. It's still just a dot of light, just like the stars, and it's still moving. In fact, most of the time for asteroids, we only see a dot of light. Unless we send a spacecraft out to them, radio telescopes can also generally get shapes of near-Earth asteroids. All right? So the distances to asteroids. Well, now that we've got telescopes, we can locate the position of an asteroid very precisely in the sky. All right? And from the positions of asteroids in the sky, we can deduce the distance or the orbits to the asteroid. Okay? The idea is, here's the Earth, we look at the asteroid. Okay? Then, a couple days later, or 15 minutes later, each step in that previous animation was about 15 minutes. So 15 minutes later, the Earth has moved a bit. Now notice I moved the Earth more than the asteroid. Why did I do that? The asteroid moves more slowly. So most of the motion of that asteroid is due to our motion. Yeah, but that's only true if the asteroid is farther from the sun, as depicted here. So as we move along, the asteroid appears to move in the sky. Based on these images in the background, that asteroid would appear to be moving. Okay? Another way to do this is, okay, can anyone, this is again a picture of an asteroid. Can anyone tell me which dot in this image is the asteroid? I can't blink this one. This telescope only took one image. Okay? No, that stands for Utah, and it's actually I think this is mislabeled. How about this? Everyone, I think you need a little bit of a break. So hold out your thumb and close your right eye and put your thumb over my face. Okay? Now isn't that much better? Okay. Now, switch eyes. Okay, you see how my face, how I jump, okay? It's very similar to what we were seeing previously with the motion of the asteroid. And this, you can see that point right there is in a different location on the two images. Yeah. Yes, that was built out of That was built out of Skylab. Okay, so yes, there's an arrow pointing that out, but can everyone see that this point is in a different location on those two images? Yeah. Are there? No, I think it's just the one. And okay, so we have UT here and HI here. What's HI? And UT is? Okay, so what does that mean? Yes, these are the locations of the two observing sites. And so an amateur astronomer I know by the name of Patrick Wiggins, we are on the phone. I was sitting right about where the third row is with a student, and we were observing with the Falks telescope, and he was in Utah, and we calculated how long it would take for us to take an image and how long it would take for him to take an image, and we basically took these two images at the same time. Okay, so that's like when you put your thumb over my face and then you switch eyes. And now, see how much it jumps when you have your thumb out at arm's length. Okay, see how much it jumps? Now bring your thumb closer. Does it jump more? Okay, and because of how much it jumps, if we can measure precisely how much it jumps, we can measure the distance to an asteroid. And I had a student last summer that we did this, and she was able to get the distance to an asteroid, the distance was known. She was able to get that to within about 2%. But when we sent it to Dr. Marco Michele, who's the real guru expert on this, he was able to get it to like 0.5% or something like that. So we can pretty precisely measure the distances of to asteroids. Usually this is not the technique we use. We usually look at the orbits, we look at the motion, because that's also giving us parallax. Okay, so here's the depiction of this. Here's Utah, here's Hawaii, or the other way around. I didn't really label them very clearly, I'm sure. Okay, so here's the asteroid, and asteroids generally are pretty dark. So you look at the asteroid, it looks like it's among these stars. From there, this person sees the asteroid among these stars. Okay, does everyone follow that? Okay, so that's one of the first pieces of information that we have is, okay, we can identify an asteroid if we look at a series of images, and then we can measure the distance to them using this parallax effect, either by taking a series of images or having a friend on another continent or another, very far away, taking pictures. Yeah, okay. Just a minute. I'm going to mute that because I'm going to talk over that. This is a very nice video that is available online. Okay, if you Google discovery of asteroids this in YouTube, this should come up, and it's by Scott Manley. So in the middle is the sun. This really quick moving one is Mercury, messenger of the gods. Venus is the next one, and then we have Earth. Okay, and this is an animation. This is 1983, 1984, and 1985. This is how many asteroids are known with that date. First thing I want you to notice is here's the Earth, and if you draw a line from the sun to the Earth, all these white flashes are discoveries of asteroids. So most of the asteroids that are being discovered are on the opposite side of the Earth from the sun. Okay? And that's because we can see them, exactly. The lit side of the asteroid is towards us, so it's like looking for a full moon. It's much easier to find the moon when it's full than when it's new. Okay? So most of these asteroids that are being detected are on the far side of the Earth from the sun. Okay? So this is 1994. We've got about 20,000. Yeah, it's going to start developing a little bit more. As we'll see in a little bit, you'll see a real distinct belt. All the dots are staying here, but they're green. They're kind of a dark green, so it's difficult to see them right now, but it will get better. Yeah. Oh, so you'll have this. Yeah. So that's probably just the direction the astronomers were looking. That you're basically you're looking at this part of the sky, and then somebody else is looking at this part of the sky, but there's a gap between what you're doing. Okay, you can start to see this belt around here, and that belt, there's Jupiter, and then there's Mercury. So this belt is between Jupiter and Mercury. Or sorry, Mars. How many mistakes do I get? Okay, so between Mars and Jupiter, and they're still discovering them. Okay, these red ones are the dangerous ones. Now watch what happens around 2009, I believe it is. You're going to see the discovery not just straight away from the Earth. It's going to be, you're going to see a band this way and a band that way. There you go. That. Does anyone know what that is? Say that louder. That's right, that's pan-stars. The idea for pan-stars was they were specifically looking for asteroids that are near-Earth asteroids, that are a threat to us. And so they decided, well, let's look. They calculated that the best place to look was in this sweet spot, sort of ahead of us and behind us. And they tried that for a while and found that actually, looking at opposition, they were finding more NEOs. And pan-stars, so far this year, and this was not even this month that I got this statistic, they had found 6 1-kilometer diameter asteroids. Okay? Before pan-stars went online, we thought all of the 1-kilometer sized NEOs had been discovered, and that they were just looking for getting the mapping down to 100 meters. Yes?
Were these new ones low albedo asteroids?
The question is, were the new 1-kilometer asteroids low albedo asteroids? I don't know. To be honest, I don't know. I'm not sure that they were. I think that we had not completely covered the phase space. And in fact, these weren't just NEOs, near-Earth asteroids. They were potentially hazardous asteroids. Potentially hazardous asteroid is one that a gravitational perturbation could deflect it into the Earth. Okay? So it's not currently en route to hit us, but it could be gravitationally perturbed to hit us. It's close enough that we need to continually watch it. Yes?
It looks like this is a giant donut. What is it? If it was in three-dimensional, would it be like Earth? It's like a big bubble that surrounds the whole star?
Okay, so the question is, what's the three-dimensional shape? It looks like a donut, and that's what it is it's like a donut. It's a belt. And so if I tilted this like this, the planets would all orbit in approximately a plane, and most of these asteroids would be in a plane. Okay. So
go in a different direction than where the asteroid belt is.
Yeah. So if you went from the sun out this way, you would have a lot lower chance of coming close to an asteroid. Now remember, these asteroids are very small compared to the space, so if you shoot something out this way, you're very unlikely to hit anything anyway. Space is really big. Okay? And you'll notice there's a bunch of NEOs here. And the other thing that I forgot to point out, and so I'll encourage you to go look at this video, really nifty video. When you see Jupiter go by, you'll see a few asteroids in front of it and behind it. Those are the Trojan asteroids, and they're in what's called a Lagrange point. So it's sort of a semi-stable point between the Earth, or between the Sun's gravity, Jupiter's gravity, and the rotation. that kind of creates this balance point it's not really a stable place, but it's more stable. It kind of captures them for a short duration. Yes.
So the asteroids that are in the red circle, are they originally gravitated from the original asteroid belt between Mars and Jupiter?
Okay, so the question is that these red asteroids, are they originally from the asteroid belt? And have they been perturbed inwards? Probably some of them have been gravitationally brought in. But those are also probably remnants from when the Earth formed. So we were bombarded very heavily. And in fact, the Earth started much smaller. It started off as a little asteroid, and then it got hit and they stuck together. And then, we kept on building up more and more material. So a lot of this is also probably material that has not yet accreted onto the Earth. Okay? Now, for their small objects, we don't mind them accreting, but big things, we don't want them to join us anymore. We're kind of snobbish that way. Okay. So there's another thing that we should mention, and that's a comet. Okay? This is an actual image of a comet that was a student down at Kamehameha Schools was working on this, and what's interesting about this particular comet is it looks like there's a double nucleus. The distinction of comets is that they kind of look fuzzy. You got this atmosphere around them when they get close enough to the sun. Okay? And so here's a better picture. This was taken by some people I know at Las Cumbres Observatories. And it appears that this is the same one because, again, it's a double comet. And so the sun heats up the ice in the comet, and it evaporates. It sublimes into a gas and forms a cloud around the comet, and that cloud gets pushed backwards. All right, so when we're talking about asteroids, the thing you need to remember about comets is, well, this is not an asteroid. Really cool. Maybe we'll do a talk on comets again sometime, maybe even sometime soon, but we're talking about asteroids today, so we'll get back to asteroids. Yeah, that's a very good lead-in. Let's take a tour of the solar system. I paid her to do that. Yes. So I'm sorry, for the virtual audience, the question was, don't comets come from much further out? Okay? And so, yes, let's take a tour of the solar system. This is an image that I found from NASA. They're talking about a specific comet in here. So this small red ring is Mars' orbit. And then we saw that the asteroid belt is mostly on the Mars side. And then Jupiter, okay? So this is sort of what's called the inner solar system. I personally wouldn't include Jupiter as the inner solar system, but maybe they are including that, maybe not. So let's go in and zoom out a little bit here. Okay, so here's our inner solar system. This is Jupiter, Saturn, go out here, Pluto. Now notice these are pretty circular orbits with the sun at the center. Pluto is kind of this oddball, isn't it? Okay. Another thing about Pluto, and I've got the podium so I can, just preach my soapbox policies. Most of our planets orbit in a plane within about 5 degrees. Pluto's tilted quite a bit up, over 20 degrees. Okay? And so this non-circular orbit, and the fact that it's made up of the same things, you see these little blue dots, those are Kuiper belt objects. Those are the beginning of the Kuiper belt. And that's where short period comets come from, is this belt, and it's very similar to the asteroid belt, except for instead of asteroids, it's potential comets. Okay? So we zoom out a little further, okay? You can see sort of the part of the orbit here. This is basically the solar system fits way inside of that little red ellipse. And there's an Oort cloud. Most of these, I think they've started discovering a few more of these. They've only discovered a few of these. These are, again, chunks of ice that orbit the sun. Unlike the asteroid belt and the Kuiper belt, this is more of a halo around us. Okay, it's not a donut. It's a sphere orbiting in every direction. Okay, and we imagine that if we passed near another star, our Kuiper belts would, or our Oort clouds would kind of mix. We'd take some of theirs, they'd take some of ours, you know, just kind of like, you know, it's kind of like a leg reading, right? Okay. So that's sort of the map of the solar system. So asteroids are the things in close to the sun, so that most of their ice probably has boiled off. Okay? If they had a lot of ice and they were closer than about Jupiter, if they're much closer than the asteroid belt, then we always see comets developing this halo and the tail. So asteroids probably don't have a lot of water. That's our observational ideas, that we see comets giving off water. And so since asteroids generally are closer to the sun and they're not evaporating, we don't think they have much water. Okay? But what are asteroids made of? Well, let's talk about meteorites. Has everyone seen a meteorite? Okay. Okay, meteorites, think of meteorites as nature's asteroid sample delivery service. Okay? Conveniently, we don't have to go out and get asteroid samples. Nature brings them to us, sometimes very dramatically. All right? And here are two meteorites, and they've been cut and polished. The one on the left is made of iron and nickel. This is about 7% of meteorites that are iron nickel. And you can see these crystalline structures in here. Those are actual crystals of nickel and iron. To make this crystal pattern like this, you have to cool the material very slow. So you take a mixture of iron and nickel that's molten, and you cool it very slowly. As in over thousands of years, you let it cool. So we don't think that this has been made here on Earth. We don't think it's pretty well determined that that's not man-made, because nobody's had the patience to do that. Okay? Probably also they saw it fall, and you'll see a black crust on the outside. Okay? And this is a stony meteorite. You see some little chondrules in there. So the stony meteorites, these are basically rock. So if you go down if you go outside and you pick up a rock, it's similar to that. All right? So that's what we see in meteorites. But how do we know what asteroids are made of? We really have not had a sample return mission. Okay? So pretty much almost all of these meteorites that we find are rock and metal. Okay? So we think that most of the asteroids are probably made of what? Rock and metal. Okay? All right. So can we tell what individual asteroids are made of? And so first of all, let's talk about color. All right? What color light are you getting from here? Blue. You're seeing more blue light than any other color. That's right. Okay. What about here? Yeah, pretend that's green because it was meant to be green. That's kind of a little off from what I expected. But okay, more red light than any other color. More green light than any other color. Okay. What color is the screen? I'm signaling to Safan. Okay, so the screen is what color? white. Okay? So, now what color is the screen? What color is the screen? White. So if we look at the color of the screen, it's actually white. Now, here's where I'm going with this. Okay, everyone see my watch? Okay. Is this a gold watch? Okay. Do we have enough light on it? Once. Okay. Rolex? No. In fact, I was doing this discussion with some students up at the summit with one of my friends, and when I got to the question of how do you know it's not a gold watch, my friend looked at me and said, "You work for the University of Hawaii." I know it's not a gold watch. Okay, so is this a gold watch? No. Okay, it could be platinum, but you know it's not gold. How do you know that this is not a gold watch? Because of the color. Okay? Now, the idea back to this, to the screen here is this. If I shine a yellow light on my watch, it might look yellow. Okay, so if we want to measure what color something really is, then we need to know what color is the light shining on it. All right? Now, this is Stephanie Spear. Let me introduce you to Stephanie. Stephanie is a student over at Kaiser High School on Oahu. And she just got back from the Intel International Science and Engineering Fair, okay, where she got a stack of awards. Very proud of Stephanie. She took first place for the state of Hawaii. And this is one of the students that I've been working with. She's been using data from the Falks telescope. So she wants to be able to measure the color of asteroids. Because just like with my watch, you know what my watch is made of because of the color. If we look at the asteroids and compare to meteorites, we can tell, we have a pretty good idea of what the asteroids are made of if we know the color. And color means brighter in one wavelength of light compared to another. So she measures the brightness of the asteroids with different filters in front of the camera. So she'll put a green filter, she'll put a red filter, and then she'll go through about 3 infrared filters, 3 different wavelengths of infrared light. And then the ratio of different wavelengths of light gives a classification system. So she actually can tell us, oh yeah, this is probably a stony asteroid, or this is a carbonaceous asteroid. Okay, so she can tell, and she's based it off of observations of meteorites here on Earth, and also Dave Tholen. Dr. Tholen is an astronomer over at Manoa. He originally did this system with a specialized set of filters that are not reproducible. Stephanie's work, she's using standard filters, and so it will make it very easy for everyone to determine what asteroids are made of. Okay? Now, do you all remember the question that Jeff Kuhn asked when Dr. Willman was giving his talk? The question was, what's the density of asteroids? Okay? We'll get to that in just a minute. Everyone likes playing games, right? Yes, we're here to have fun. We're going to play a game. Okay, this is a model of an asteroid. Okay, 4 different models. And these are, what I've done is I've plotted, well, I didn't do this. This was Dr. Lacerda that actually did this. What he's done is he's plotted how bright the asteroid would appear. Remember, asteroids are single points. We cannot resolve them. So how bright the asteroid would appear against time. And so this asteroid would be bright, 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 drop down in brightness to about half as bright, and then come back up bright, 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 drop down, come back up, bright, bright, bright. All right? Okay, and this one is constantly changing. Now, you look at these asteroid pictures, these are the asteroids which are rotating, right? Okay, so they're changing in how bright they are. Can you guys match one of these four with one of these four? Yeah. 1 and C. Does everyone agree? No. 1 and D. Does everyone agree with 1D? Okay. 4 and C. Yeah, so 1 is D, 4 is C. 2 is B, correct? And 3 is A. Yeah. Very common mistake between confusing these two. Okay, so number 1, D. Number 2 is B. And no. 3 is A. 3 is A. Okay, bright, 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 dip, bright, 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 dip, bright, bright, bright. Okay, so bright, 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 dip. Okay, so 3 is A, 2 is B, 1 is D, 4 is C. All right, everyone agree with that? Well, here's the question. Here's what we're really going to be asking ourselves is, can you tell me from this graph now how long it takes for the asteroid to turn around one time? Okay, so for this asteroid it has to go through 1 dip, 2 dips. Okay, so this is 1 full rotation. It goes through 1 dip, 2 dip, and then back up to a peak. All right, does everyone understand the logic there? So we can measure how long it takes for an asteroid to turn around. Isn't that just what you were dreaming of learning today? Didn't you wake up going, gosh, I wish I knew that? Yes, Aaron. That is once, okay? So, okay, it'll be easy to tell because my right hand will stay my right hand, okay? Here's the idea, is you've got the 2 asteroids. We're doing 2, okay? And and they're contact, so they're barely touching, and then they're rotating around. Okay, there's 1, or there's 1/2, and there's, okay? So 1 bright, 2 bright, back to the beginning, okay? I work for the University of Hawaii. 20 times, you say? Okay. So here's the neat thing. So we can go out and we can look at asteroids and we can tell how fast they're rotating. Okay, assuming they don't have some weird rotation pattern, which some of them do, and that's an entirely different lecture. But we can plot, each one of these points is 1 asteroid. So an asteroid, this asteroid rotates at, you didn't see me drop, right? Okay, it rotates about 10 times per day. So this is the frequency. 0.1 means it rotates 10 times per day. Okay. Okay. Or sorry, this is 10 days. It's 10 days. And this would be 10 times per day. So I've got that had that backwards. So this asteroid, it takes 10 days for it to turn around once. Yeah, it's 1/10 of a time per day, correct. Okay, and then this asteroid goes around 10 times per day. All right, this is the diameter of the asteroid. Okay, so this asteroid is a little bit smaller than 1 kilometer, right here, a bit smaller than 1 kilometer. Okay, and this one takes 100 days to rotate, exactly. All right, so very interesting. We put all these scatter plot, and then this line develops. Does that line bother anyone? Yeah. Yeah, and an asteroid smaller than about, 100 meters, they can go up above that. But these asteroids can't. They can't rotate faster than that. Why? Wait, except for this guy, this lonely guy here. Yes, he's an individual. That one's an individual. Yeah. You've basically got it. So, okay, so that bothers people. That's good because it bothered me. So let's think about this. Here's an asteroid, and we put a marble on there. Okay, so this is an asteroid. Looks like an asteroid with a pimple is what someone was telling me the other day. It's an asteroid with a marble on top. That marble is what we call a test particle in physics and astronomy. And let's imagine the asteroid rotating. All right? So if we rotate that asteroid too fast, what's going to happen? This test particle is not going to stay on top of the asteroid anymore, is it? Okay. So what's holding it onto the asteroid? Gravity holds that test particle onto the asteroid. And then one way to think about it is centripetal acceleration is kind of acting outward. Actually, what we really need to do is have gravity large enough that it can accelerate it in the circle. Okay? So, okay, now I'm going to warn you. Everyone grab their seat. You're going to see math. You won't have to do the math, but I'm going to show you some math. Okay? All right? And there's at least one or two students in here who will be doing this math later this week, or sometime next week. Anyway, okay, so let's assume that asteroids have a constant density. Okay, does everyone know what I mean by density? Okay, so density is how much mass per unit space, how much stuff there is in a volume. Okay, so assume a constant density. This is what the g is gravity. This is the acceleration rate of gravity, and it's proportional to the mass divided by the radius squared. The mass is 4/3 pi r cubed times the density. Boils down to about like this. Okay. Don't worry, there's not a quiz on this. Okay? Now the acceleration rate that you have to apply to that particle to keep it going in a circle is the velocity squared divided by the radius. And that boils down to the rotation rate squared times the radius. Okay? So let's take this and make it equal to that. What that will be is that's the point at which this barely stays on top of the asteroid. If it rotates any faster, then it doesn't maintain contact with the surface. Okay, does everyone understand that? Okay, and that looks like this. I've got radius and radius to the first power on both sides. Well, what happens when we have radius and radius on both sides? Who's learning algebra? Yeah, they'll cancel out. So the rotation rate doesn't depend on radius. The rotation rate that this test particle will fly off does not depend on radius if we assume that the density is constant. Okay, what did we see in that chart? We saw a horizontal line where we didn't spin any faster. So if an asteroid is actually made up of a bunch of particles being held together by gravity as a pile of rubble, then if it spins any faster, what will happen? Spin apart, okay? So we just learned two very interesting things from this thought experiment, from that graph and this thought experiment. The first is we can now calculate what the density of an asteroid is. We can get an idea of how dense they are. And if you put reasonable numbers in for this, it comes out to be somewhere between water and rock. Okay? somewhere in there, somewhere in that range. There are some other details. Okay, and yeah, it's not a gas. It's not. It's not iron, but I mean, it's not real. It's a lighter rock. Yeah, it's something like a lighter rock, which is about what you'd expect for a pile of gravel. Okay. And the other thing that we learned is that most large asteroids are not single chunks. Okay? If they were single chunks, they could rotate faster. Okay? Because then, you know, I can't pull this into two pieces. So I can rotate it much faster and it will stay together because it's one piece.
The outlier is probably much denser.
So that outlier, well, no, the outlier is probably a single chunk. Okay, so it does not have, it's not like this where there's two pieces that can fly apart. Yes, it is held together more by chemical bonds. Okay, it's the physical structure of the asteroid that's holding it together rather than the gravitational. So it's electromagnetic force. Okay. So this is, let me introduce you to my niece. Somehow she got time on one of some of the telescopes here. I think her uncle knows a guy. This is Kelsey. This is my niece, Kelsey Barber. And so what she did is, this was again her science fair project, and she took first place for Earth and Space Science in the Ricci Science Fair. That's the Northern Utah Science and Engineering Fair. So she took a series of images of an asteroid, okay? And then she measures how bright the asteroid is in each picture. And then you look for a periodic signal. What does that look like? Yeah, it looks like the asteroid is spinning. And sure enough, so what is one period? Okay, we'll start here and tell me stop when I get to one period. That's right. So from here to here, that's one time around. She was looking at large asteroids to see if she could find another large monolithic, so in other words, single piece asteroid, an asteroid that's spinning too fast for it to be held together by gravity. Okay? So, as a summary, asteroids are sort of these snowy dirt balls that orbit the sun. When I was in high school, asteroids were rocks, comets were dirty snowballs. Now, asteroids are snowy dirt balls. Okay? So they've got some water and ice still left inside, and we're beginning to see every now and then one of the main belt asteroids will kind of start outgassing, and then we call it a main belt comet. There's been about half a dozen to a dozen of those. But mostly asteroids are basically just these snowy dirt balls. For reasons I really didn't go over so far, they are what is left over from when the planets formed. Okay? They're made of silicates, metals, and other trace amounts of materials. There will be organic compounds, carbon-based compounds. There will be probably some water, ammonia, dry ice, so what an astronomer calls ice. And by measuring the color, we can tell what the majority of that is made of. We can tell if it's generally a stony asteroid or an iron asteroid or a carbonaceous asteroid. There are sort of three major classes. And most of the large asteroids are rubble piles. How did we determine that most of the large asteroids are probably rubble piles? Because of the spin. Could we be wrong? Yes, we could be wrong. But we've only found one that we are pretty sure is not a rubble pile. Okay? That outlier, that one outlier. Now the smaller asteroids, yeah, you do have monolithic small asteroids. And large, small is about 100 meters in diameter. That's the dividing point. All right. So one of the things that I loved was, if I've been able to see further, it is by standing on ye shoulders of giants. I copied and pasted the quote. Nice try. Yes, so this is the spelling that was used. So spell check Newton. This is what Isaac Newton said. Oh yeah, spelled as okay. That one's me, Isaac. Okay, so Isaac Newton. I will fix that. And so, while I do think these two have stood on the shoulders of giants, I think they've stood pretty tall on their own. So let's give them a hand. And thank you. No, they haven't been standing on my shoulders. I just, I'm a troublemaker. You know that, Aaron. Yes.
Two questions. First one, not entirely serious. Am I right in saying that asteroids are basically rock or metal?
Okay, so the first question is, are asteroids basically rock or metal?
I have a supplementary.
Okay.
Have any been found that are either easy listening, country, or classical?
Okay, and are any easy listening, country or classical? Okay. No, most of them are Rolling Stones.
Yourself of all mistakes.
Serious question. You say meteorites are the delivery system for asteroids, yeah?
Right, so yes, meteorites are the delivery system, nature's delivery system for asteroid samples.
So for the crystallized metal, for the nickel-iron crystals,
Mhm.
you've got to have 1,000 years or thousands of years of nickel-iron at a very stable temperature, which implies a fairly large structure. What is that structure, and were there planetoids, were there whatever? Because I've
Okay.
never heard that.
So the question is, for these nickel-iron asteroids, we have this crystalline structure which has to cool over, say, 1,000 or more years. So that implies a fairly large structure, okay? And it would have been like a planetoid or a very large asteroid. In fact, all of the metal asteroids probably are from the center of a much larger object, and the rock was also metal, or was also molten. The rock floated to the top, the metal condensed down in the middle, and then there was kind of a transition region where you had rock with globs of metal, or metal with globs of rock, and we see these in asteroid samples. We see rocks with little pieces of metal, and we'll see metal with little pieces of rock. And then after it cooled, something big hit it and broke it into a bunch of pieces. And that's what we see.
Has anybody done any work on sort of what size these planetoids would have been?
I believe there has been someone who has done work on what the size of the planetoids would be. I am not familiar with that work. So the question is, has anyone carbon dated these meteorites? We don't carbon date them, but yes, we do look at radioactive decays. Aaron, I'll let Aaron answer this. He probably knows. Right, for it to be carbon datable, it has to be organic material. The way carbon dating works is you have carbon-13 in the atmosphere that's absorbed into your body, and then that decays. Okay. Do the asteroids coincide with Big Bang is your rationale. I'll get there. Do you know, Connor? Yes, they coincide with the formation of the solar system. Do you know how they dated them? Okay, So they actually, it's similar to carbon dating. It's actually a radioactive decay. We look for other radioactive isotopes, and you can find them in places that they don't belong, effectively. So if you find say, lead where you should have found uranium, okay, then you know that was a uranium atom that decayed into lead. And by knowing the decay rates, then you can effectively date these back, and it sort of coincides with about the formation of the solar system. The number that is coming to my mind is about 4.5 billion years. The solar system's a little older than that, though. So these are objects that are, primordial to the formation of the solar system. Yeah. Let me go with her, and then there. Okay. Could I finish explaining carbon dating? Right. Okay. So carbon, the stable isotope of carbon is carbon-12. So there are 12 particles in the nucleus. But carbon dioxide in the atmosphere, the sun, there's the solar wind can form carbon-13, which is carbon what? Carbon-14. I think you may be right. It's carbon-14. So it's carbon with 2 extra neutrons. Okay? That carbon isotope decays, and we know how long it takes to decay. So what we'll do is when we find, say, some organic material that we want to figure out how old it was when it died. So we find a piece of wood, and we want to know how old was that tree when it died, and it was pulling carbon out of the atmosphere. We know how long it takes for these carbon atoms to decay back into carbon-12. And we know about how many the ratio in the air. So you start off with a known quantity of carbon-14, known quantity of carbon-12, and then over time, the carbon-14 turns into carbon-12. So by measuring how much carbon-12 and how much carbon-14 there is in this material, you've got a way of measuring back, thousands of years. Yeah. Okay. All right. Yes.
Have they been able to identify asteroids with certain types of metals or other high-value items that would make it economically feasible to go mine?
Right. So the question is, have they been able to identify asteroids with metals and high-value items? So you're talking about the gold, the platinum, and the idea is to mine them. And I don't think they've specifically been able to identify gold or platinum, because gold and platinum are fairly rare. But all of the gold and platinum on the Earth was delivered to us by meteorites. Okay, the gold and platinum at the surface of the Earth came to us after the Earth cooled and then was deposited in the solid structure. Okay? Right, because if the Earth is molten, any gold would sink to the bottom. So until the Earth's crust cooled, there was no gold at the surface, no platinum at the surface. So all the platinum and gold that we're digging out of the ground is from a meteorite. And so probably what we want to do is we want to look at the denser denser asteroids, probably look at the iron ones. They're more, I would imagine that they are more likely to contain platinum and gold and other materials. But some of the stony ones might very well have those materials as well. Okay. No, I don't think they've identified any specific ones. They have identified, I think asteroid Nil-Boone is an iron, and it's kind of a bone shape. But they've identified some metal asteroids and some stony asteroids, and different types of stone as well. Okay. Aaron, did you have a question, or?
It's unrelated, but just out of curiosity, how many, I forget if it was several million or several 100,000 years
So how long after the formation of the universe was were objects able to form? If I give you a number, I'm going to be wrong, but it's not very long. It's, I'm guessing less than 500 million years before we're starting to see galaxies. But someone please check that. Before you quote me, go check that, Google that. Okay? Yes?
We've seen close-up pictures of some of the bigger asteroids, like Cirrus,
Mm-hmm.
and they look like they have pukas on them that are like impact craters. They're all speckled with.
Yes.
If they're really agglomerations of gravel, how come those impacts didn't break them apart like breaking a rack of balls on a pool table?
Okay, so the question is that we have these high-resolution images of asteroids, and I had a picture of Eros. Let's go up to the picture of Eros. Okay. And so the question is, we see these impact craters, and those are these dots are in fact impact craters. These are where something is smacked into it. And so if this is a rubble pile, why didn't that ruin it? Why didn't that break it into a bunch of pieces? And also, how was the house able to survive? The house was built after all of the craters. Okay. And so if this is assuming that this is a rubble pile, this may not be a rubble pile, but let's assume this is. Well, the Earth, the surface of the Earth is a rubble pile, right? And if I go out and I take a handful of sand, that's, not held tightly onto the Earth. So if an asteroid comes and hits, and a meteorite hits the Earth, why does that sand not go flying off into space? Because of gravity. And the gravity is often strong enough to hold it together. But you will lose considerable amounts of material. Probably a lot of the material in that crater would have been lost. Okay, so you do lose material, but it's just, it doesn't, blow it apart spectacularly like Star Wars would display. Okay? Yes, they do not have a garage on this particular property. If you're in the market for a house with a garage, I can look for one for you. My sister is, in fact, a real estate agent. I'll get you her business card. Okay, let's go back here.
Oh, did you guys watch a program the other night on what killed the dinosaurs? And to make a long story short,
Mm-hmm.
they figured out it was an asteroid because they could detect iridium in layers that spread out
Mm-hmm.
from North Yucatan there. So I guess some of them contain iridium, which is a pretty heavy metal.
Yes. Yes. So the question is, so far as the dinosaurs, we believe were killed by an asteroid strike, a meteorite strike, and the way that we determine that is at about the same time that all the dinosaurs died, we find a layer of soil that's very rich in iridium. Iridium is very dense, and so it would have sunk to the center of the Earth when the Earth was molten. And so seeing this layer of soil that's rich in iridium is an indicator of an asteroid strike. We also have found the crater. We think we found the crater that is associated with that. Okay? So does that answer?
Do most of these asteroids contain iridium? And I guess my question is, where did the iridium come from? It obviously came from a star, but can you tell how many generations?
Okay, so the question is, do most asteroids have iridium? And there's the second part. The most asteroids, I would say it's more common in asteroids than it is on the surface of the Earth, because it's, we have the surface of the Earth here, and then the iridium that we have here came from asteroids enriching this the silicates at the surface of the Earth. And at least that asteroid was probably quite rich in iridium. Okay, and second is the second part of your question is, where did that iridium come from? Did it have to go through generations of stars? Probably did not have to go through multiple generations of stars. So iridium is formed, hydrogen is fused into helium, helium's fused into carbon, blah, 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 all the way up to iron. Once you get to iron, it doesn't give off energy to make heavier elements. And exactly, it stops. You remembered from class. Okay. Another one of my former Astronomy 110 students. I've got a couple of them in the room. So anything heavier than iron actually sucks up energy. So that doesn't form until you get the supernova, and it blows apart. You have the iron being hit by heavy amounts of radiation, and it gets converted into heavier elements through a lot, mostly I believe through alpha captures. Okay. Yes.
Questions. Okay, so the asteroids contain these heavy metals and stuff that come, sound like they come from stars, so it must explode
Mm-hmm.
after the Earth was developed and formed. Do other solar systems have
I mean-
asteroid belts? Not after, before the Earth was formed.
Yeah.
Well, I think it takes millions of years for it to reach us.
Okay.
We only have a billion
So-
solar system.
So the question was basically that do other stars have asteroid belts? But the first thing is, so the Earth was formed out of the same material as the sun, okay, and it formed at the same time. So in the sun, we see silicon, we see magnesium, we see all these heavier elements that make up the Earth. Most of the hydrogen and helium that was associated with the heavy elements here on Earth were blown away. When the sun started as a star, all that hydrogen and helium that was in a disk around the sun was just pushed out. Okay? Jupiter became heavy enough early enough that it was able to start sucking up, and it was able to gravitationally retain the hydrogen and helium. That's why Jupiter, Saturn, Uranus, and Neptune are mostly made of hydrogen, or have a lot of hydrogen and helium. Jupiter's mostly hydrogen and helium, but at the core you'll find silicon and iron and all those other materials. So, do other stars have asteroid belts? Almost certainly, and I would expect almost every one of them. Okay? The reason is that if they have silicon and iron and all these other elements in the materials that collapse down to form those stars, then those materials would have probably have formed into asteroids and would be orbiting them unless something perturbed them out of their orbits. Very, very old stars, which are very metal poor, and warning, do not tell your chemistry teacher this. I'm an astronomer. There's hydrogen, there's helium, and then there are metals. Okay? The reason is that hydrogen and helium, from what we are seeing, hydrogen and helium are really the only two elements that existed when the universe was formed. Trace amounts of lithium, very, 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 and I mean, just nothing, practically nothing else. So all these heavier materials formed in a star. So if you find a star that's really old, say a red dwarf that can live 100 billion years, maybe you're not going to find an asteroid belt around that, unless it captured one from somebody else. But for stars with metallicities like the sun, the metal quantities like the sun, I would expect definitely asteroid belts, and for most other stars, I would expect asteroid belts. Okay.
So, just to
In there.
clarify, I've only just finally twigged something. So the asteroid, what size of a body would it make?
If we added all of the mass of the known asteroids, what size body would it make? I'm not sure if we quite reach Mercury.
So it's still very small.
Yeah, it's kind of too small to be a planet. Okay, it's not a lot of mass, and most of it is in Ceres. Which there's a planetoid called Ceres, and that's like the biggest asteroid. Okay, I know I've skipped you about 3 times.
There's a large asteroid belt surrounding a supernova.
Mm-hmm.
Supernova exploded, and the asteroid belt would it be swept away almost not too long after the explosion, or would it take a much larger amount of time?
So we're talking about an asteroid belt around a star that goes supernova. And would the asteroids be swept out immediately, or would it take a long time? They would be vaporized, most likely, because think about how bright a supernova is. A supernova can be as bright as its entire host galaxy, right? Okay, so something that close in, well, rock will melt. In fact, rock will evaporate. Iron will melt. Iron will evaporate. Tungsten will evaporate. Okay? Once you get tungsten evaporating, you're done. So yeah, it would be able to evaporate these asteroids, and then that gas would just be swept out with the other material. Okay. It would be a plasma. It would be a plasma. All right. Did you have a question? Someone else had a question. Okay. You had one more.
You mentioned that gravitational perturbation could cause an asteroid to zonk us someday. What would cause that type of perturbation?
Okay, so the idea, the question is, and I think you're relating it back to the potentially hazardous asteroids. These are asteroids that a gravitational perturbation could alter their orbit sufficiently to hit us. So what would cause that sort of gravitational perturbation? And that would probably be, well, a lot of people like to blame Jupiter, okay? But potentially the other planets could as well, or maybe even a very close pass to a smaller asteroid. But collisions, yeah. So you could also have collisional exchange of kinetic energy, and they could be knocked into our path. Yeah, but again, asteroids are small, space is big. You don't have a lot of collisions. There was actually one discovered with one of the Falks telescopes. I think it was Falks South, which I wouldn't mention if I wasn't fairly certain, because Falks North is my favorite and therefore much superior. And if Mark is listening, well, I'm sorry. You're a good man. I know the site manager of Falks South. He's a good guy. Keeps a good telescope, but don't let him know that. All right. So yeah, but collisions are very uncommon because space is big, stuff is small, but they have been seen. They have been seen in the past. All right. Have I bored you to tears yet? One more, another question. Okay.
So if two asteroids, one's big and one gets hit on the tail end, would it increase the spin?
So if 2 asteroids collide, would it increase the spin? Well, okay. So this asteroid is spinning this way. Let's say this other asteroid comes in and hits it like this. That'll slow it down. Or it might reverse it. If it comes in and it hits it like that, it'll increase the spin. So it's sometimes yes, sometimes no. Sometimes it will spin it up. Sometimes it'll spin it down. Sometimes it'll change the rotational axis. Sometimes it won't change it. It depends on the impact. Mm-hmm. A lot of people have trouble with that graph and that flat line as a limit. So he was referring back to the flat line, yeah. And here we go. Yeah, this is the point. And so his comment is he has really a lot of trouble with this graph. Okay? I do too. All right. But let's say we have an asteroid here, and let's say that it's made of a rubble pile. This asteroid up here doesn't have enough gravity to hold itself together.
Or the rubber pile just flies out, and there's not and the force is dispersed, so it can't speed up momentum.
Yeah.
Yeah, it gets smaller.
Yeah.
It gets smaller, so
Then it becomes, so it flows
Yeah. So this asteroid here would become these two asteroids over here. Okay? Is that okay? Yes.
Is the asteroid belt stationary or is it orbiting the sun?
The asteroid belt does orbit the sun. It just like it's not a solid structure. It's here's an asteroid, and this asteroid is say this big in scale. The next one is over there in Longs. Okay, space is big, stuff is small. That's my favorite. Yeah, exactly. Okay, so it's not. There's no structure to the asteroid belt. And they're very widely spaced. And if they didn't orbit the sun, well, the sun has gravity and they would just fall in. So they do orbit, and they have mostly circular orbits. Okay, yeah.
An iron asteroid, as it spins faster, can it induce electromagnetism?
So if you spin an asteroid faster, can it induce electromagnetism? Well, I mean, if you've got an iron asteroid, I guess you could have, an electric current in there. It really doesn't, though. Yeah. Yeah. Yeah, if you had an iron meteor or asteroid that had a permanent magnetic dipole moment, exactly what you're talking about. So it was a permanent magnet. Then that spinning, yeah, it would generate a magnetic or an electric field around it. And in fact, it would give off very small amounts of very long wave radio waves and all sorts of fun things like that. But it wouldn't, like generate lightning or anything.
Yeah, if there's a
Yeah.
small asteroid piggyback to it,
Mm-hmm.
and they're both spinning at the same time, and there's an induced electromagnetism, will there be
Well,
stability?
so you're looking for a way for the asteroid to be stuck together using electromagnetic. In that case, I wouldn't rely on spinning to generate the magnetic field. I would just say, okay, let's make it a permanent magnet and another permanent magnet. Click, there they are. They'll stick together. Just be as permanent magnets. You don't want to have to go into creating an electromagnet because then you have to keep that electricity flowing and just have two permanent magnets if you want to do that. I think that, well, let's put it this way. I'm sure it exists somewhere because nature has just really amazed us about how much it knows. It made lasers long before we ever thought of the idea. The things we find in nature are very surprising. So I'm sure somewhere there is an asteroid that is being held together because it's two magnets. But they're very rare.